Unless you're a pirate, odds are you use a stereo camera every single day.
Right here on your face.
Your eyeballs are essentially two bog standard cameras placed alongside each other. This is precisely what a stereo camera is. Our brains have learned where each eyeball is relative to the other one. This distance right here. Whenever we see something, our brain does a continuous calculation where it matches a point it sees in one eye, for example my big schnoz, to the same point in the other eye. Because this distance is known, it can then triangulate where that big schnoz is in 3D space, and then get an idea of how far it is away from us. Here's a basic outline of how stereo cameras do what our brain does.
Step 1. Snap 2 images using 2 cameras of the same scene.
Step 2. Find a feature, my schnoz, in the left image, and then locate the same feature in the right image.
Also, take note of how many pixels the feature in the right image is shifted over by.
A good way of thinking about this is by holding your finger
In front of your eyes and change which eye you look through, it'll look like the finger jumps around quite a lot, whereas objects in the back of the room will stay pretty much still.
Step 3. Repeat Step 2 for every pixel in the image. Step 4. Generate a disparity map. This is basically like a picture where instead of representing color, each pixel represents the distance its corresponding partner pixel is shifted across in the other image. Conventionally, dark colors represent pixels that were found close together and thus represent objects in the background, and light pixels represent objects that were found far apart, relating to objects in the foreground.
This disparate information is then fed into this equation, where x is the focal length of the camera, b is the baseline, in other words, the distance between two cameras, and z is the disparity. Chuck it in there, distance.